Thermochemistry is the study of the transfer of energy in chemical reactions. In this discussion, we're going to simplify matters by looking simply at the energy content of the reactants in the chemical reaction and comparing that to the energy content of the products of the reaction. There are two possible outcomes. The first one at the top, in the top section here, the energy, the free energy, the potential energy of the reactants is higher than that of the products. So you can imagine then the reaction going downhill. This is given the term an exergonic or an exothermic reaction if you're talking in terms of the heat. So if heat is released, this would be referred to as an exothermic reaction, one that gives off energy going from that higher energy reactant to the lower energy product. At the bottom, we have just the opposite, where the reactants are at the lower energy state and the products are at the higher energy state. So in this case, we're rolling the ball uphill. We've got to add energy in order to bump the energy of the reactants up to the level of the energy of the products. And this is referred to as an endergonic reaction. And again, if we're thinking in terms of the heat, heat would have to be added, making this an endothermic reaction. So just what happens in a chemical reaction that either requires or gives off energy? Well, if we start with a chemical change, we know that a chemical change involves the breaking and forming of bonds. So breaking bonds and forming bonds. Usually what you've got to do to start a reaction is to break bonds. So you're going to break the bonds in the reactants. Breaking bonds is always an energy requiring process. You always have to add energy to break bonds. To separate things apart, you have to add energy. And the forming of bonds is always going to give off energy. So from the energy standpoint, the breaking of bonds is going to involve adding energy in order to break those bonds. And when we form the new bonds, we're going to give energy off. So that exergonic or endogonic reaction depends on the amount of energy we have to put in to break the bonds versus the amount of energy we get out when we form the new bonds. Now, if we look a little deeper into bonding, bonding in reality deals with the rearrangement of electrons. So often that rearrangement of the electrons or the gain or loss of electrons is very directly involved in the energy being released or absorbed by a reaction. So here we have a reaction between methane and chlorine forming methyl chloride and hydrogen chloride. So what would we need to do in order to figure out the energy change involved in this reaction? Well, the first thing we need to do is figure out what bonds are being broken over on the reactant side. So if we go through our Lewis dot structure process, we would end up with a structure for methane that looks like this, and for the chlorine that looked like this. Likewise, on our product side, we would have carbon, and then our hydrogens, again, using our dot structures. And then our hydrogen chloride, like this. So these would be the bonds that are involved in the reactants and the products. So we can see that in our reactants, we're going to have to break off one of those hydrogens, and we're going to have to break apart the two chlorines, And then over on the product side, we're going to form a bond between the carbon and the chlorine and between a hydrogen and a chlorine. Right? So now it's a matter of finding out how much energy it takes to do that. So here we have a table of average bond energies. It says average because the energy it takes to break the bond is in some cases going to depend on, or I should say in all cases, is going to depend on the other atoms that are bonded to each of the atoms that you're breaking apart. But this will give us a general idea of what that energy would be. So we saw that we need to break a carbon to hydrogen bond. And we're going to need to break a chlorine to chlorine bond. Let's see, where are we going to find chlorine to chlorine? Right here. And we're going to form a carbon to chlorine bond and a hydrogen to chlorine bond. Where's the hydrogen to chlorine bond? Right there. So those are the bond energies that we're going to need. Now these are given in kilojoules per mole. A mole is a particular number of molecules or a particular number of things. So we'll take a look back at the reaction and see what this does. So here I filled in the energies that we're going to need to break our bonds. So here's the carbon to hydrogen bond, chlorine to chlorine bond, and on the product side, the bonds that we're going to form over here. And again, remember that the energy that we need to break the bonds it's always energy we have to put in. And when we form bonds, that's always energy that we get out. So if we add together those energies, we get a total of 657 kilojoules required to break all the bonds on the reactant side, and 770 kilojoules of energy that will be released on the product side. Now, if we take a look at those two numbers, we should see that we have a net gain of energy. If I find the difference between these two, I get a net gain in energy of 123 kilojoules. The negative sign here reflects that energy is released. So the system, this reaction gave off that energy. So it would be an exergonic or exothermic type of reaction. Here we'll take a brief look at the application of this to a biological system, the conversion of ATP to ADP to release some energy in the cell. Now, the reactions in cells, particularly those involving the energy, transfer of energy, get rather complex. So we'll just take a quick look at this and see what we can come up with. The first thing we'll notice is that we have to break off one of the phosphate groups from the ATP. So we're going to have to break apart the bond between the phosphorus and the oxygen there in order to end up with what we have down here in the ADP. So obviously that's going to require some energy to be put in. So where does the energy come from that we get out of converting the ATP to the ADP? Well, we've got to look at a little more bonding that's happening there. You notice that over on the on the reactant side, we have water, right? So we might want to kind of keep in mind that water molecules look like this. So there's a couple of bonds there that we may have to break in order to have this function. And if we look over on the product side, we've got this stuff over here. So why don't we use our VSEPR and we'll or our Lewis dot, and we'll come up with a structure for that hydrogen phosphate molecule or ion. All right, so here we have the phosphate ion, and if we take a quick look back over to our original ATP that we broke off, notice that we broke it off between the phosphorus and the oxygen. So if we look over at the products again, the molecule that we drew for the structure we drew for the hydrogen phosphate, we must have made this bond right here. Okay, so that bond between the phosphorus and that OH must have been formed there. Well, that needed to have come from the water molecule that we started with. So let's go back over to the reactants, and we're going to need to break apart that water molecule there in order to form that new bond in the hydrogen phosphate group there. Okay. So that adds another bond that we had to break over on the reactant side, but now we can see one of the bonds that gets formed over on the product side. The other part to this is that we have that hydrogen ion that is also available to react in this situation. So when you take all of the energy changes that are going to occur from the breaking and forming the bonds, you have a net production of about 7.3 kilocalories per mole of ATP that gets converted to ADP. So by breaking that bond in the ATP and forming the new bond in the ADP, you're going to end up with a net surplus of energy that will then be available for use in the cell for some other process. So just to kind of refresh our memory here, the breaking of bonds always requires energy to be added in order to break bonds. The forming of new bonds will always give off energy. Oftentimes, bonding involves the transfer or rearrangement of electrons, which is very important in terms of that energy process. And we want to keep in mind that the overall reaction has the potential to either go downhill, be exergonic, in other words, the reactants start out at a higher energy level than the products due to the arrangement of the bonds in the atoms, or the reaction could be endergonic, meaning that in order to get from the reactants to the products, you're going to have to put energy in to go to a higher state due to the arrangement of the electrons and the bonding that's involved.